Hey everybody, Dr. A here, and in this video we're going to be providing some background information on transverse shear stress. So let's go ahead and get started. Transverse shear stress, which we call tau, is also known as beam shear stress, and it occurs in cross sections subject to a shear force V. So let's go ahead and write down the governing formula for transverse shear stress. It's going to be tau equal to VQ over IT, okay? So that's shear force V, same V that we see here, times capital Q divided by capital I times little t. Now, in a few minutes later in this video, we're going to define more clearly each of these four terms. But for now, we just need to write down that transverse shear stress is equal to VQ divided by IT. Now, you might be wondering, how is this different than average shear stress that we learned earlier in one of our previous videos? Now, you might recall that average shear stress that we learned at the beginning of this playlist in Mechanics of Materials is equal to V over A, okay? Now, we learned that this is valid for very small cross sections. And we commonly see this in bolts and pins, okay? Bolts and pins. And so what happens is whenever you have a very small cross section, okay, the distribution of shear stress can simply be determined by taking an applied shear force and dividing it by that small cross section. Now, as your cross section gets larger or becomes more complicated in what it's and how it's shaped, this V over A is not really going to cut it for calculating the shear stress over an entire cross section. That's where we need to use this formula, VQ over IT, okay? And so what we're going to be talking about for the rest of this video is VQ over IT, not V over A, which again is valid for only really small cross sections like what you see with bolt and pin connections, okay? So let's go ahead and dive a little deeper into beam shear stress, or what we sometimes call transverse shear stress. So I want us to consider a beam subject to a shear force V with a rectangular cross section. So here in this left diagram, we're going to be looking at a side view of this kind of beam. And we see that we have this internal shear force V, okay? Now, I drew it a little bit of a distance away from this section of the beam because I'm going to draw a little bit more information here in a minute. So if you're writing this in your notes, draw this vector V a little bit of a distance away from the face of this beam. Now, this dashed line right here represents the beam's neutral axis, which we abbreviate NA. Now, the neutral axis of a beam is where we define Y bar, or the centroid, okay? So we can call this Y bar right here, okay? And if you recall from your knowledge of flexural stress, we could call this Y bar bottom, and we could call this up here Y bar top. Either way, Y bar, whether you're looking at from the top datum or a bottom datum, is defining our neutral axis of the beam, okay? So, which is our centroid. That's the centroid of the beam. So this is a side view. Now over here, I have this 3D view, all right? So I'll make a note here. This is supposed to be a 3D view of that same beam. And so here's that same shear force V that we see hanging out here near our side view. And if you look inside of the cross section, we see this rectangle based on the sentence above. We're given a rectangular cross section for now. The thickness of the beam is T, little t, okay? Now it turns out this little t is the same little t that we saw in the denominator of our governing formula earlier, and I'm going to talk a little bit more about that here in the next few minutes. All right, and then the neutral axis in the cross section of the beam is given here by this dashed line labeled NA. So of course, you know, I could still label this dimension right here as Y bar top and this dimension down here as Y bar bottom. And of course, that's the same neutral axis and the same Y bar bottom and Y bar top as I see in my side view, okay? So let's define these terms a little bit more explicitly, right? Tau is equal to VQ over IT. We need to remember that formula, okay? V is the internal shear force at a point along the beam's length, okay? How do we get V? Well, you can get it by using method of sections or drawing the shear force diagram, okay? So all V is the internal shear force, and we know how to get that from our knowledge of statics. Again, just method of sections or drawing the shear force diagram. What about that capital Q in the governing formula? This is what we call the first area moment, and it's going to be equal to Y prime times Y bar prime, okay? A prime times, sorry, I may have said that wrong. A prime times Y bar prime. That's what capital Q is, okay? Now, I have a whole nother video where we only explain Q, because the hardest part or the most confusing part about this process tends to be calculating Q. When people are learning this for the first time, Q seems to be the most confusing part when this is a new topic for people. So I have a whole nother video dedicated just for Q, okay? So I'm not gonna dive into that right now. I'm just gonna give you the basic definition. It's what's called the first area moment, and it's equal to an A prime times a Y bar prime, and that's gonna have units of length cubed. It's not a volume, okay? It's an area moment, all right? Now, what about I? I is the second area moment, which we know, aka as the moment of inertia about the neutral axis, okay? So this is the moment of inertia about the neutral axis. This is the same I value that we learn in statics, okay? So if you have a single rectangle, what is I about its neutral axis? Well, it's BH cubed over 12, right? Now, if you have a composite shape, you use the parallel axis theorem where you add a plus AD squared, okay? So if you're a little rusty on that, take a look at my statics playlist, because I have a few videos where we go over how to calculate I. But again, that is a statics topic, okay? It's the moment of inertia, just like you learned in your statics class. Now, T is a member thickness, okay? Member thickness at a particular part of the cross section. Okay, so in our illustration here with a rectangular beam, T is just this T here, which is a uniform thickness, right? If you have a rectangle, it has the same thickness no matter where you look at this in the cross section, all right? So again, I'm going to rewrite our governing formula here. You know, tau is VQ over IT. Now, if I were to sketch the shape of this shear stress distribution in the cross section, what would that look like? Well, it would be in the plane of the cross section, okay? Remember, shear stress is causing a slicing effect in the cross section. So it's in the plane of the cross section. So I'm going to sketch this. I'm going to use green here, and I'm going to sketch it kind of like this. Okay? So these are like little vector arrows slicing through the cross section, okay? So how is that shape going to be? Well, it turns out tau max in the cross section will occur at the neutral axis, okay? So I'm going to make a note here. I'm going to say tau equals tau max at the neutral axis, okay? Now, we can pretty much say that this is true majority of the time. For the majority of beams that are out there in the world, tau max occurs at the neutral axis, okay, where the centroid of the cross section is. There are a few very unique specific beams that have very weird geometries that this might not always be true, but I'm going to say 99.9% of the time this is true, okay? So we're going to just go with this for the purposes of our lesson in mechanics of materials. Tau is tau max at the neutral axis, okay? Now, tau is going to be 0 at the beam edges on the top and bottom surfaces. So I'm going to make a note here. I'm going to say tau equals 0 at the beam top and bottom surfaces, okay? Now, I'm going to say the distribution of tau is going to be parabolic, or it's going to be segmented parabolic, okay? So watch this. That means that the magnitude of tau is going to look a lot like this, okay? So, I didn't mean to scroll there. So the magnitude of tau is going to look a lot like this parabolic shape, all right? So here at the top and bottom edges, tau is 0, tau is 0, and then at the neutral axis, this is going to be tau max, all right? Now, here's the thing to be careful about, okay? Remember, tau is going to be lying in the plane of the cross section because it's slicing through the cross section. This curve right here is just meant to show you the magnitude of tau and how it's varying throughout the cross section. So it's not really appropriate to put arrows here. We're not going to put arrows here, okay? Because arrows would indicate, if you threw some arrows on here, that would indicate that tau is normal to the cross section, and that's really not what we're showing right now. We're just showing the shape of the shear stress distribution at a plane in a cross section, okay? So if I move over here in my 3D view, all right, I'm going to have a maximum tau at the neutral axis. But then as I get away from the neutral axis, I'm going to draw my little vector arrows a lot smaller, okay? And I'm doing that to show that as I get farther away from the neutral axis, that shear stress tau, its magnitude is decreasing until we finally get to these top and bottom edges where tau is 0. Okay, and so I can make a note here, you know, tau equals 0 at this top edge and tau equals 0 at the bottom edge. And then at the neutral axis, you have tau max. All right, so again, we're showing kind of the same information we have on this side view. And the distribution is going to be curved. It's going to be like a parabola there, or quadratic, okay? So that's for a rectangular cross section, all right? Let's dig a little bit deeper. We often have beams where we don't have a rectangular cross section, right? We often have T shapes, I shapes, C shapes, L shapes, so on, okay? So let's talk about composite shapes, okay? So we're going to say composite shape cross sections, okay? So when you have a composite shape cross section like a T shape or an I shape, whatever, we're going to make a note here. We're going to say there is an abrupt change in the distribution of tau at flange web interfaces. This is caused by the abrupt change in thickness, little t. All right, so what do we mean by that? Well, let's look at a T-shape, for example, okay? So let's say you have a beam, and let's say that you have a T-shape like this. Draw that a little bit better for us. Okay. So the top, more horizontal portion of the T-shape, this is called the flange, okay? So we call this the flange, all right? And then the more vertical portion of the T-shape, that's this kind of rectangular portion right here, that is called the web, all right? And so here you have this interface, okay? This right here is the flange web interface, okay? And so you notice here, you have an abrupt change in the cross-section thickness, little t, right? So down here, when you're in the web, you have a thickness of the web, all right? So let's label that thickness W, thickness of the web. But in the flange, this is going to be a different thickness, okay? I'm going to call this thickness of the flange, okay? Now, I want to make a side note here for my civil engineers who are watching this. The people in civil engineering, when you get to a steel design course, the term thickness of the flange is going to refer to something a little bit different. It's going to refer to this dimension of the flange. When I say thickness of the flange in this video, I'm referring to the thickness in VQ over IT, okay? I'm referring to specifically the horizontal thickness for now, okay? So any civil engineers watching this, if you're saying, ooh, Dr. A did something wrong here, this is my disclaimer. I'm using this label to mean this horizontal thickness on purpose. It's not the same TF that you would see in a steel design course, okay? So what happens is when you are calculating tau as VQ over IT, right? I'll make a, rewrite it here so we remember VQ over IT. You notice this thickness T changes very abruptly at this flange web interface, right? So it goes from, if you're down in the web, the thickness is very small, and then you jump up to the flange and the thickness is much bigger, or you go in the other direction, okay? And so when that thickness abruptly changes in this denominator, tau is going to abruptly change. All right, so I'm going to go ahead and sketch a side view of this same beam, okay? And I'm going to try to line these edges up together, okay? All right, now the neutral axis for a T-shape is going to be somewhere, it depends on what all these dimensions are, but let's say that neutral axis is like right here, okay? There's the neutral axis, all right? And let's say, there's our shear force V again, all right? And so what is the distribution of the shear stress tau going to be here? Well, you're still going to get this kind of parabolic segment. Okay, let me draw it a little bit better. All right, you're going to get this kind of parabolic segment in the flange, and it's still going to be, you know, tau is equal to 0 at this top edge here, and you get this parabolic increase. Okay. Now, what's going to happen next? Let me erase this NA and relabel it. Maybe right here, just so it's out of the way. So what's going to happen is you will get an abrupt jump upwards in that shear stress once you get to that interface, okay? You're going to get an abrupt jump upwards. It's going to get higher, and then you're going to get another parabolic shape that will go back to 0 at the bottom face, okay? So there's tau equals 0. Now, where is tau max? Well, again, tau max is still going to occur right here at the neutral axis, okay? So here is tau max, all right? So here you have these kind of two nonlinear curved distributions with an abrupt jump at the flange web interface. Now, why is that? Again, we see T changes abruptly, okay? So in the flange up here, okay, the thickness is much bigger, all right? And so you have a big number in the denominator here. And so that means that tau is smaller in the flange. And then all of a sudden you cross this interface and you get into the web, okay? Now the web thickness is much smaller than the flange thickness. So you get a smaller number in this denominator, which does what to tau? Makes tau get bigger, and that's where you get this abrupt jump upwards. And you get a little bit of an increase until you get to the neutral axis where tau max is, and then you kind of decrease back down to 0 at the bottom edge, okay? So let's do another little exercise. What if we had an I shape, okay? So here's what I would encourage you to do. Maybe pause the video and you see if you can sketch out what you think an I shape shear stress distribution would look like. Okay, pause the video and see what you get, and then, you know, compare it to what I'm about to draw now. All right. So let's say here is the, you know, neutral axis. All right, and you know, you've got two flanges now, right? So you've got a top flange, you've got a bottom flange, and then of course, you know, you have the web, all right? And we're gonna go ahead and draw the side dimensions of this beam. Look at a side view. Okay, so what do we think? And then of course, you know, you have this shear force being applied. So what do we think the distribution of the shear stress is going to be here? Well, you know, you're going to have this kind of parabolic increase, all right, in the flange, and then you're going to have an abrupt jump upwards, and then you're going to have this parabolic shape in the web, and then you get down to the bottom flange, which is much thicker than the web, and you're going to have this abrupt jump back down. Oh, didn't mean to scroll there. And then you're going to have this parabolic or nonlinear curve back to 0 at the bottom surface. Let me draw that a little bit better for us. Right there. So again, you've got tau equals 0 at the top and bottom edges, and then tau max is going to be at that neutral axis, okay? And so each one of these curves is like a little segment of a parabola, but you've got these abrupt jumps or discontinuities at the flange web interfaces, okay? So that's pretty much the shape of that. Now, again, what direction is this shear stress going? Well, of course, it's in the plane of the cross section, okay? It's in the plane of the cross section. So the shear stress is actually trying to slice through the cross section. But remember what I have in green here, these curves, that's just the shape that's outlining the magnitude of tau as we go through the cross section. Tau is not sticking out of the cross section, okay? It's in the plane of the cross section. This is just meant to give us the distribution of tau within the cross section. So showing how its magnitude is varying, all right? So that concludes this video. This was, again, a lot of background information on transverse shear stress. And then we have another whole video on just how to calculate Q. Again, I mentioned before, Q seems to be a point of confusion when people are learning this for the first time. So we need to take a look at that video. So thanks for watching. And if you found this helpful, please hit like and subscribe.